Today we talk about projectile motion. And in a sense, we've been talking about this for a number of days. Projectile motion is simply the motion of objects near the surface of the Earth where one has constant acceleration down. And we've been talking about that, but we've been sort of slowly bringing ourselves toward this most generic case. And just to tell you, spoiler alert, what the one extra piece that we're going to deal with today is that we'll allow for the objects to have an initial velocity vector that is at an angle relative to the horizontal or to the vertical. So we learned before that acceleration points down, and therefore if you choose your coordinate system such that, for example, the y-axis points down, then it divides up into constant acceleration in the vertical direction and constant velocity in the horizontal. So all of that's fine. It's just that the problems are going to be a little bit more complicated because we have to deal with an initial velocity vector that doesn't point in only one of those directions. So I'll talk a little bit more about that, about how free fall connects with this topic. Much of that is just a review. I just want to sort of drill that into you. And then we'll do one example, which is a grasshopper leaping off a cliff. I should also mention that this will be the last topic of so-called kinematics. So in the next topic, we'll move on to the primary topic of this course, which is Newton's laws. So now that we've understood how objects move through space, the kinematics description of objects, then we can use that to write down the laws of nature, the laws of motion, which are Newton's laws. And in a sense, the next lecture that we see, Newton's laws, will be enough to describe all of motion of mechanics. So I could just let you go after that. You could figure everything else out from there. Of course, we'll spend time developing that slowly, but that's where we are. We're at the end of kinematics. So, as I said, projectile motion is not really anything new. In fact, I could have called the last three lectures free fall. I think the 3 lectures ago, we talked about one-dimensional motion of objects with constant velocity or constant acceleration. And that's often in introductory physics called kinematics, although we know that kinematics is just simply the description of any motion. So you have equations that deal with constant velocity, constant acceleration, and when we did this type of problem, we talked about objects that were moving just on a straight line, like a car that's maybe accelerating along the highway here. So it has an initial velocity vector that looks like this, and then it also has an acceleration vector that looks like this, and so at some time later it would have a larger velocity, and you would be able to compare the distance traveled to the time. So we've done problems like that. Then in the next lecture, we introduced so-called free fall as an example of motion with constant acceleration. So we know that on the surface of the Earth, so if you're close to the surface of the Earth, that you have an acceleration vector for all objects that points downward, and its value, its magnitude, is going to be equal to 9.8 meters per second squared. So if I draw the acceleration vector of some object, maybe it's an apple falling out of a tree, then that object will be moving downward, started from rest, and because the acceleration points down, then the velocity in the next moment will point down, and it will move with 9.8 meters per second squared, which we say is called g. And what we mean by 9.8 meters per second squared is that if it falls from rest, after 1 second, it will be moving with 9.8 meters per second velocity. And after 2 seconds, it'll be moving with twice that, so almost 20 meters per second. So that's what we used for free fall, and we did problems that were basically aligned only along the the vertical axis, which you might call the y-axis. Then in the last lecture, we did what I called 2D kinematics, which was basically a simplified version of today's lecture, the motion of projectiles, but we only allowed for objects that were moving with an initial velocity vector that had a horizontal component. So we talked about like the cliff diver that was moving, that jumped off the cliff completely horizontally, and then after that point, their motion was dictated by the acceleration due to gravity, which points downward, and their trajectory would look something like this. And of course we saw that you can divide up their motion into a constant velocity horizontally and a constant acceleration vertically, and then you connect some initial point to some final point, and you can solve problems like that. So today we talk about generic projectile motion, so the motion of objects in free fall, where they can have any initial conditions. So that we're not going to restrict ourselves anymore to just horizontal velocities or just vertical velocities. So that what that does is it means that the initial velocity is going to appear in both your y equation, your constant acceleration equation, and in your x equation. And we'll talk about how to deal with that. But let's talk about it a little bit qualitatively first. So we're going to look at an object that jumps off a cliff, and as we'll see, it turns out that the motion of objects is well described by a parabola. So the path that the object takes will look something like this. And we know that the velocity vector is always tangent to the path. So let's draw that initial velocity vector. It's going to look something like this. It must be tangent to the path, and then depending on its magnitude, it will have some length. So that's what the initial velocity vector looks like. And the whole point of these problems is that because the acceleration vector points downward with magnitude g, 9.8 meters per second squared, that we can look at a coordinate system where the y motion, completely separate from the x motion, the y motion is constant acceleration and the x motion is constant velocity. So let's just examine what that means for this velocity vector, just very qualitatively. Well, in the equations, we wrote it as, for constant velocity, we had an equation for the velocity which was that the velocity at any time is equal to the initial velocity in the x direction. That's what we mean by constant velocity. And for motion with constant acceleration, we had that the velocity at any time was equal to the initial plus the acceleration times time. So whatever the value of the y component of the acceleration, here you can see that since I've chosen a y axis pointing upward, that the acceleration in the y direction will be negative. So this will be a negative number. You'll see that the velocity is always changing in the negative direction. So something that has a positive value initially will be losing a little bit every moment in time. Eventually it'll go to 0, and then it'll become more and more negative. We can see that happening on the picture here. But if we look at the component of this vector, let me just give ourselves a whole coordinate system here. To find the components, you project back to each axis. So this number here is what we call the x component of the initial velocity vector. And then you project back to the y-axis, and you get to this tick mark, and that's what we call the y component of the initial velocity vector. And today we'll do that. We'll use that little triangle that you can see for the initial velocity vector in order to determine its components and then plug them into these equations. But what's interesting is that you can see that there's like this is what you could call the v0x distance. Sorry, it's not a distance, it's just the absolute value of v0x. And if these equations are true up here, And if it's really true that we can separate out the y motion from the x motion, then I should be able to draw qualitatively the velocity vector at any moment along this path. Because I know two things. One is that the velocity vector will always point tangent to the path, and the other is that this size of the x component will never change. It will always be the same. So let's try it. Let's try a couple little points here. So let's say it's at that point in time. Well, I know that the velocity vector will be tangent to the path, so I could sort of draw a line that's tangent to the path. And then I also know that the value of the initial velocity in the x direction will never change. So that means that there's going to be some distance here. Not distance, I keep saying distance, but these are velocities. So v0x will be maintained, and therefore I could draw that its tip should be like this. So that should be the velocity vector at the next moment in time. We could look at another one. So let's look at the top. So at the top, the tangent is exactly horizontal. And what is its length going to be? Well, its length is going to be completely determined by the initial velocity in the x direction. So that's going to be exactly this vector here. What happens as it goes down? Well, if we take this moment in time, then the tangent looks something like that, maybe. And we know that the x component doesn't change, so we're going to get some v0x, which is going to look like that. So that means that this will be the tip of the vector. So that will be our velocity vector at some moment on its way down. And you can see that that v0y is just getting larger and larger as it goes down, but the v0x stays exactly the same. So I think it's just nice to sort of see that qualitatively before we just start plugging in numbers. And it's good to remember that your equation tells you that the horizontal velocity remains constant, but it's good to remember what that means in terms of the picture, that you could always sort of look at those components of the velocity vectors and see that the x is staying the same. In this example, we have a grasshopper that leaps into the air from the edge of a vertical cliff. And it has an initial velocity which is set at an angle with respect to horizontal. And then we're given the maximum height above the cliff, and we're given the distance that it travels horizontally, meaning the distance from the bottom of the cliff where it lands. So let's just draw a picture of this. So we have a cliff, and then we're told that it's some flat field after the cliff. So it just moves like this. And then we have the grasshopper. Oh dear, am I really going to try and do this? It's like the key characteristic of a grasshopper, those big legs, right? There's a grasshopper. It's green. Got to take the time to make it green. Oh, it's like big fat thighs, right? Grasshopper. There's our grasshopper. I guess it needs to have some sort of little things here. And it has an initial velocity which is directed at an angle. So I'm going to draw that initial velocity vector. I think that's a little bit too steep. So it's just above 45 degrees, 50 degrees we're told. And I'm going to label it. It is my v0 vector. And do we know its magnitude? We do not. So I'm going to give it a name, v0, but I don't, oops, it's not 0, but I don't know what its magnitude is. I can, however, label the angle that it makes with respect to the horizontal, because we were given that. So I'm going to give that as well. Put that over here. Okay. Now we were told that it's going to reach some maximum height. We were given that distance, and then it's going to land somewhere on the plane down below. So let's first draw the trajectory of the particle, the path that it's going to take. And we know that this path is going to be somehow parabolic. So do our best to try and make it look like a parabola. Now we can see exactly what that maximum height is. It's something like this distance here, and I can give that a name. Let's call it little h, and we're told that that's going to be 6 centimeters. So let's do everything in meters. So it's 0.06 meters. And we are also told the distance that it lands from the cliff wall. So let's call this capital D, and that's 1 meter. And this is like where it lands. We can call the time here t hit. We don't know what that time is. Is there anything else that we can label here? Well, I guess we want to find the height of the cliff. That's one of the questions that's being asked. And we also want to find the initial speed. So we've already given a name to the initial speed. Let's now give a name to the height of the cliff. So call it capital H. We don't know what that is. Is there anything else we need to put on our picture? Well, the key fact is that from the moment that it leaves the ground, it will be in free fall. So its motion is completely determined by this vector, the acceleration, 9.8 down. Maybe that's it. Is that all that we need? We're asked to find the height, we're asked to find the initial speed, we have names for those things, we've shown what the path looks like, and we've labeled everything else. Now we need to give ourselves a coordinate system. So as we've said before, you can choose any coordinate system you want, but some are better than others, and in particular here we really should choose one that has a y-axis pointing along the acceleration vector. I'm going to do that here. And I'm going to put the y-axis pointing along the cliff wall, and I'll put it pointing upward. And then we can choose the origin of that coordinate system, and I'm just going to choose the origin to be right where the grasshopper starts. And that will be my x-axis. And finally, remember we're going to be, the method here, now that we've done the picture, now that we've done the coordinate system, the method is simply to start writing down some equations. Writing down the equations of constant velocity and constant acceleration for the horizontal and vertical motion respectively. And remember what those equations mean. They relate an initial moment in time to a final moment in time along the path. So that's why we drew the path, so that we can look at those moments in time. And it's a good idea to sort of label points along the path and then use those equations from those points, from one point to another. So I'm going to call this point A, and then I'm going to call the top, where it reaches the height that we were given, I'm going to call that point B. And I'll call this point C, where it hits the ground. I think those are probably the key moments that we want to deal with. So now we know how we're going to relate our equations. So, okay, so method is we just start writing things down. So we were told that it's going to reach this height, and I know some things about the grasshopper. Well, I guess I only know that it's going to reach that height. I also know that at this moment in time, the velocity vector is going to be horizontal, so that might help me. So let's try and use an equation that relates these two moments in time. And let's use the vertical position equation. So we have y is equal to y0 plus v0y t plus 1/2 ay t squared. So constant acceleration in the vertical direction. And as I pointed out in the picture, I'm going to use it from the initial moment in time to the peak of its flight. That's from point A to point B. And now I just go through looking at my picture, writing down what these quantities are. So y means final height, so that means the value of y at point B. So I look at my y-axis, I project point B back to the y-axis, I land here, and that means that I've landed at h, little h. Y0, well, that is the y position at point A, and that's just the origin, so that's going to be equal to 0. The initial velocity in the y direction. Okay, now this is the new piece. So in previous questions, you could just look at that velocity vector and say, well, it's only in the x or it's only in the y, and therefore it's plus or minus the magnitude or 0. Here, we actually have to find its component. So let's draw that. So we'll draw the coordinate system again, meaning we draw the x and the y pointing in the direction that they are. And we'll draw the initial velocity vector, because we're going to find its components. And we'll label that angle 50 degrees, and then we find its components. So this is v0x. We don't need that yet, but what we're looking for is v0y. So we're looking for that number. So remember back from the very first lecture how we find components of a vector. Well, we draw it on a coordinate system like this, and then we draw another little triangle with our theta inside of it, and the hypotenuse is labeled by the magnitude of the vector, and then I just call the horizontal x and the vertical y. Now I'm going to find x and y. Remember what we're interested in. We're interested in the y component of the initial velocity vector. So that's going to be this number, and it's positive, so it'll be equal to y. Just a side note, if it happened that the initial velocity vector was pointing down, then v0y would be a negative number. So that's why I make a difference between the variable v0y and the variable y. On a triangle, these are always positive numbers, but my components could be positive or negative. So I'll always find positive numbers from my triangle, and then I have to look back and see what I should actually plug in for the component. I don't really need to worry about that here, but it's good to keep that in mind. So what do we have? If I want to find y, then I use opposite over hypotenuse. So sine theta is equal to y over v0. That comes out of the triangle. Or y is equal to v0 sine theta. And v0y is just equal to y. I'm not really going to write that down. So because y we think of sometimes as a distance, here this y is not the same thing as this y over here. Not enough variables to represent the things I want. Okay, so now we can plug in. So we were given, or we found, that v0y is equal to v0 sine theta. Then we have a t. So we have t, and what is that? Well, I didn't give a name for that yet. I guess I should probably do that. So I called the t at point C t hit. Let's call this t top. And I do not know what its value is, so I'll just put t top. Then I have 1/2, the y component of the acceleration. Well, the acceleration vector points downward. If I place that on a xy coordinate system, it's going to have a negative y component equal to its magnitude, so it's going to be minus g. So there we go. That's our first equation. Now the next step usually is to put a box around it, so try and write it a little bit nicer. So we get h is equal to, I usually like to put things in front of the trigonometric functions, and then take the minus signs out. So this is my boxed equation. Oh, terrible box. Okay. So that's the procedure. You write down an equation, you plug in based on what your picture tells you, and then you make the equation look nice. The point is that we now have an equation that relates quantities in the problem that we've named. Some of them we know, some of them we don't know. So let's quickly take a look, because it's at this point that you want to decide whether you're done or not, whether you've solved the problem. So what are our unknowns? Well, we don't know this t-top. We don't know the initial velocity. We do know the angle, and we do know little h, and of course we know g, but we have two unknowns and one equation. So that means we are not done at all. We need to keep going and try and find another equation. Okay, so let's try and see what we can do. Let's try a different equation on the same path. How about the, well, let's use that one that takes time out of it. So I'm not happy that I had to deal with time here. Maybe I can get away with not dealing with time at all. So that equation is vy squared minus v0y squared is equal to 2ay y minus y0. And I'm going to use that on exactly the same segment of the path, so from the leap, point A, to the top, point B. And now we go back and look at our picture and see what the values of those things are. So Vy means the final y component of the velocity. And let's just sketch what that looks like from what we did on the last page. We know that this distance is preserved. Remember, not a distance, but a velocity component. But that x component of the velocity will be the same all the way through the motion. So I know that this velocity vector is going to be both horizontal and have an x component which is exactly the same as the initial. So that's what it's going to look like at that point. Well, what is the y component of that velocity vector? That's what we're looking for. Well, obviously it's 0. That velocity vector points along the x-axis. So that's a nice fact that we can use, which is that when you get to the top of the motion, the y component of the velocity is 0. So that's going to be 0. Then we have v0y. Well, we already found that. I mean, we at least wrote it down. And we wrote it down as v0 sine theta. So I can write that as v0 sine theta squared. And then we keep going. So we have 2 times ay. We also found that. It's negative and it's equal to minus g. And then y final and y0, we also found those. So y final is h and y initial is 0. So we get that. So what does that give us? Well, we have, just making things look nice, Siri's getting upset with me, v0 squared sine squared theta is equal to, I'm multiplying both sides by minus 1, 2gh. Okay, so we get another boxed equation. So again, let's take a look and see what we know. Well, we know h, we know g, we know theta. We do not know v0. But look at that. We only have one unknown in this equation. So that means that we can actually solve for it. So let's try it. So v0 is equal to 2gh over sine squared theta with a square root. I did a few steps of algebra there. You should probably write it out yourself. I should probably check to make sure it's correct. 2gh divided by sine squared theta, and then take the square root of both sides. Yeah, looks good. And now we can plug that into our calculator. So let's take a look. So we have 2 times 9.8 times the height, which was 6 centimeters, 0.06, is that right? 6 centimeters. And then we divide by sine of the initial angle, the angle of the initial velocity vector, which was 50 degrees. And then we square that thing. And then we take the square root of the whole thing. So I get 1.42 approximately. And that's nice. We found the first thing that we were asked. What is the initial speed of the grasshopper? So notice where it came about. We have an initial velocity, which is at an angle. We wrote down an equation that only deals with the y component, and we were asked by that equation to write down the y component of the initial velocity vector. We did that in terms of its magnitude. So we found that the y component is equal to v0 sine theta. Since we know that angle, we were able to find the magnitude. So that's the importance of writing everything in variables, giving names to these positive quantities, whether you know them or not, is that in the end you can solve for those positive quantities. Okay, so we're not done with the problem because we haven't found what? Well, we haven't found this height. So we know the distance that it's going to travel, but we haven't yet found the height. So let's write down some more equations. Now, obviously, we're going from point A to point C here, so we want to change the path that we look at with our equations. But again, we're going to use the same kind of equations. So, so I guess I'll put that little thing there. I should say, I don't necessarily know what I'm going to get when I start writing things down. I didn't necessarily know that I would be able to find the initial velocity by writing down an equation that went from here to here. I just started writing down equations that related things that I knew and hoped that I could get somewhere. So you shouldn't always think of the problems as being completely linear, that you need to find part A before you find part B. Instead, you should use the method. Draw the picture, name the variables, write down equations and see what you get. And you might find part C before you find part A. It might turn out that way. So don't worry so much about that, and don't panic, because you can always just write down all of the equations and find anything you want. So let's do the y position equation again. But in this case, I'm going to apply it from the leap to the landing on the ground, so from point A to point C. So just to remind you, we're going all the way along the path from here to here. Because of the way these equations work, I don't have to worry about anything in the middle. I only have to worry about the initial and the final point. So what do we get? Well, the final point was at the bottom of the cliff. So y final is at the bottom of the cliff. So what is that? Well, that is the y position of point C, which if I project back to the y-axis, I land here. That is going to be a negative number because this is the origin, and it's going to be a negative number equal to minus h. So I plug in minus h for y. Y initial, well, we started at the origin, so that one's again 0. v0y, we already found that. It's going to be plus v0 sine theta. And t is going to be what I called t hit here. Then we have 1/2 ay. Again, a points down, so its component is minus g. And then we have t hit squared. So this is an equation. What can we get with that? Well, let's add the last term to both sides. So we get 1/2 g t hit squared minus h is equal to v0 t hit sine of theta. Okay. Can I use that equation yet? Well, I have how many unknowns? I don't know t hit, and I don't know h. So that means I cannot solve anything yet with that equation, even though I now know the speed, the initial speed, and the angle. So let's continue. Notice that we haven't used one piece of information here, and that is the horizontal distance that it traveled. So let's try and use that. So to use the horizontal distance, I'm going to use an equation of constant velocity, because motion in the horizontal is governed by constant velocity. And I'm going to use it on the same path. So from the leap, point A, to landing on the ground, point C. So what is x final? Going back and looking at it, well, that's going to be this point on the x-axis, and that's exactly this distance, capital D. So I can write capital D. X initial, we started from the origin, so that's going to be equal to 0. V0x, I don't think I found that yet, but we can see what it is because we did this work over here. So we use this triangle to find that the y component of the initial velocity vector is equal to v0 sine theta. And if you do exactly the same procedure with cosine, so cosine theta is equal to x over v naught, and that means that x is equal to v naught cosine theta. And v0x, as we see from this picture, is a positive number on the positive x-axis, so therefore it's just going to be equal to this length on the triangle. So I can plug in for v0x, v0 cosine theta. So we get v0 cosine theta here. And then t, well, that's the amount of time it takes to hit.
Sorry, I missed that. Could you say it again, please?
No, I haven't done with you, Siri. Okay, so what does this do? Well, let's make a nice boxed equation out of it. Well, that's going to be d is equal to v0 t hit. I don't know what I'm saying that Siri's so interested in. Okay. So, what's going on with that equation? Well, we know d, we know v0, we don't know t hit, but we know everything else. So that's great. So that means we can solve for t hit. And once we have t hit, we can plug that back into this equation, and then we can solve for capital H. So let's do it. So that second equation gives us t hit is equal to d over v0 cosine theta. And then we plug in. So we have d was 1 meter. Divide that by v0, which we found already, and that was 1.42 meters per second. And then we divide by cosine of theta, and theta was 50 degrees. So we get 1.1, approximately 1.1 seconds. That's the time. We weren't asked for the time, so I'm not going to put a box around that. But now we can plug into our other equation. So 1/2 g t hit. Well, let's solve that in algebra first. So what am I looking for in that equation? I'm looking for h. So that equation says h is equal to adding h to both sides and then subtracting this piece off. It's going to be equal to 1/2 gt hit squared minus v0 t hit sine of theta. That's what h is going to be. So I can just plug that in. So I get 1/2 times 9.8 times t hit squared, the one that I just found, 1.1 seconds. And then I subtract v0, which was, what was it? 1.42 times t hit, 1.1, times sine of my angle of my initial velocity vector, which was 50 degrees, and I get 4.72 meters. And that's the answer to part B. So we found the initial velocity magnitude to be 1.4 meters per second. We found this, and we found it from the height that it had to go. And then from the distance that it traveled, we found the height of the vertical cliff. All right, see you next time.